Hi, Assalamualaikum and a very good morning. So now we are in chapter 3, the periodic table. And now we're going to focus on the subtopic of 3.2 periodicity, part 3 of the video. So in this video, we're going to learn about the definition of the first and second ionization energy. Next, we're going to explain the variation in the first ionization energy across a period and down the group. So the period that we're going to focus on is in period 2 as well as in period 3. And most of the discussion will be about the first ionization energy, elektron pertama yang dikeluarkan daripada atom tersebut. And this learning outcome of A and B will be covered in this video, which is in part 3. So, without any further ado, let us start. So, ionization energy. Ionization energy is basically a minimum energy that is required to remove 1 mole of electron from a gaseous atom or ion. So there are going to be two definitions that we need to focus, which is the first ionization energy and the second ionization energy. And the ionization energy here means it is an energy that is required to remove 1 mole of electron from the atom. So this concept is similar to what you have learned in chapter 2. Okay? And the first here means electron yang pertama dikeluarkan. And the second means the second electron that's going to be removed. Okay, so let us look into the definition for the first ionization energy first. So the first ionization energy are the minimum energy required to remove 1 mole of electron from the outermost orbital in 1 mole of neutral gaseous atom. For example, if you have X gaseous atom, when you remove 1 mole of electron, you're gonna convert the gaseous atom into gaseous ions. Okay, and this process here requires absorption of energy. Okay, so energy need to be provided so that the electron will have enough energy to be promoted to the higher and the highest energy level, which is n equal to infinity, so that it can be removed from the atom. Okay, and that is why the charge here going to be positive. So for example, for this one, let's say if we have magnesium gaseous atom, so once we remove 1 mole of electron, we're going to get magnesium gaseous ion. Okay, so the charge here going to be 0 and the charge here going to be 0 as well. Meanwhile, the second ionization energy is the energy required to remove. Okay, similar thing, the minimum also. The minimum energy required to remove 1 mole of electron from 1 mole of the positive ion in the gaseous state. So we need to start from the positive ion. Okay, so let's say here we have X plus gaseous ion. When it removes another electron, the second electron, it's going to become X2 plus gaseous ion. And this requires another mole of energy. So for example here, you can use magnesium gaseous ion. Okay, and now you wanted to remove another electron. Okay, so when you remove another electron, you're going to get magnesium 2 plus gaseous ion plus another electron. So the charges that you're going to get here is positive 1, and then here we're going to be positive 1 as well. So the charges here is still maintained and balanced. Okay, so first adalah elektron yang pertama, second adalah elektron yang kedua, dan dia start daripada gaseous ion. Alright. Now, there are 3 factors that affect the ionization energy. So first we have the atomic radius, next we have effective nuclear charge, and the third one we have the shielding effect, or known as the screening effect. So for atomic radius, so the larger the atomic radius, it means that the electron, the valence electron, will have a lower attraction towards the nucleus. So when it gets a lower attraction towards the nucleus, it means that it is larger in size, and hence it is easier to remove the electron. So when it is easier to remove the electron, we can say that it's going to possess a lower ionization energy. Okay, for the second factors, which is the effective nuclear charge, you can say that when the ZEF increases, the attraction between the valence electron and the nucleus will get stronger. So when the attraction is stronger, means the size will get smaller. Okay, so because of a very strong attraction, it is very, very difficult for 1 mole of electron to be removed. Hence, more energy is required to remove 1 mole of electron. Hence, you can say that the ionization energy increases. Okay, now is the shielding effect. So, when you say that the shielding effect increases, you know that the mutual repulsion will get increases as well. Okay, so when the repulsion increases, the valence electron and the nucleus will be less attracted, and hence it will be the valence electron will be further apart from the nucleus, and it is very, very easy to remove 1 mole of electron. So when it is very easy to remove an electron, the ionization energy gonna get down. Okay, now we're gonna look into the variation of the first ionization energy across a period. And the first ionization energy means elektron yang pertama sahaja yang kita akan tengok. Alright, so as what you can see here for the atomic radii, as what you have learned in the previous part, you will know that across a period, the proton number increases, right? And as a result, the effective nuclear charge will increases as well, and the atomic radii will get smaller and smaller and smaller. So when the atomic radii get smaller and smaller and smaller, the valence electron will be closer to the nucleus, and the force of attraction is very high. So when the force of attraction is very, very high, it is very, very difficult to remove 1 mole of electron, and hence more energy is required to remove the electrons. So the ionization energy will increases across a period. So you can say that when the proton number increases from this part to the other part here, the effective nuclear charge increases, and hence the nucleus attractions towards valence electron will get stronger, and the atomic size decreases. That's what we have learned. And the more energy is needed to remove an electron from the outermost shell. And as a result, the ionization energy will increase as well. Okay, so you can specify here to be the first ionization energy. Okay, and from the explanation here, you will expect the ionization energy for the, okay, let us look into the period 2 first. So you can say that the ionization energy of the neon will be higher than fluorine, oxygen, nitrogen, carbon, boron, beryllium, and lithium. Okay, so you know that the neon will have the highest ionization energy because it is the smallest in size. Meanwhile, the lithium will have the lowest ionization energy because it is the largest in size. Okay, so this is the general expectation that you're going to see. But in actuality, what you're going to get is to be something like this. So the sequence is a little bit odd. So the differences occurs at this part here as well as at this part here. Okay, it happens at group 13 and group 2. Same goes to here, group 16 and group 15. So there is a shift in the position. The question is, why? Okay, why does this happen? Okay, before we answer that, let us look into period 3. So generally, it's gonna follow the similar thing. The argon gonna be the highest ionization energy, and the sodium gonna be the lowest ionization energy. So we're gonna get the trend to be something like this. So highest ionization energy, and this one is the lowest ionization energy. And because argon here gonna be the smallest in size. Okay, but in actuality, what's gonna happen here is that they're gonna be a shifting in position as well at this part and at this part here. And again, it happens at group 2 and at group 13. And it also happened at group 15 and group 16, okay, in the similar group but in different period. So why is this happening? To answer that, let us look into the next slide. Okay, so as what you can see here, we will expect the actual line to be a straight line. Okay, but because of anomaly, we can see that the group 2 and the group 13 here is very odd because the group 2 going to be higher than the group 13. Similarly to here, where group 15 going to be higher than group 16. Okay, similar to here, group 15 and then group 16 here. Okay, so we suppose it to be a straight line. Okay, this is what we're supposed to predict: sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. But then, because of anomaly, the magnesium appears to be higher, and then phosphorus appear to be higher, so that it becomes to be something like this. Okay, and on the next slide, we're going to learn why. So let us focus on the period 2 first, and this is the graph that we have looked just now. So we're going to look at the anomaly between group 2 beryllium and group 13 boron here. So in order to understand why the ionization energy of the group 2 is higher than group 13, we need to look into the electronic configuration. So for beryllium, beryllium has 4 electrons. So the electronic configuration is going to be 1s2, 2s2, and it is a completely filled orbital. And for boron, it has 5 electrons. So it's going to have an electronic configuration of 1s2, 2s2, and 2p1. And as what you can see here, the 2p1 is a partially filled orbital. You can also draw this thing in terms of orbital diagram. Okay, so beryllium 1s2, 2s2, you can see that it is a completely filled orbital of the 2s. Meanwhile, for boron, it is a partially filled orbital of the 2p. Okay, so you can say that the completely filled orbital of the 2s in beryllium is more stable than partially filled orbital of 2p in boron. So, removing an electron from the completely filled orbital of 2s of beryllium makes the atom less stable, and this is unfavorable process. And because of this, more energy is needed to remove the electron from the stable state, which is from the beryllium. And hence, this is why the ionization energy of beryllium is higher than boron. Okay, now we are still in period 2, but now we're going to explain the anomaly that happened between nitrogen and oxygen. Okay, so the nitrogen is in group 15 and the oxygen is in group 16. Similarly, we're going to explain that using the electronic configuration. So for the nitrogen, it has 7 electrons. So the electronic configuration is going to be 1s2, 2s2, and 2p3, which is a half-filled orbital. And then for oxygen, it has 8 electrons, 8 electrons. So you're going to write the SPDF notation going to be 1s2, 2s2, 2p4, which is a partially filled orbital. Okay, so in order to look more about their half filled and partially filled, it is better for you to draw the orbital diagram. So as what you can see in the nitrogen, the 2p orbital will have a half filled orbital at the 2p part here. So the completely filled orbital gonna look something like this. Okay, which is 3d6 is complete, 3p6, 2p6 is a completely filled orbital. Okay, but 2p3 gonna be the partially filled, which is stable as well. Meanwhile, the 2p4 is a partially filled orbital and it is less stable in comparison to half-filled orbital. So you can say that the half-filled orbital of the 2n in nitrogen is more stable than partially filled orbital of 2p in oxygen. Hence, you can say that the removing an electron from the half-filled p orbital in nitrogen makes the atom less stable, and this is unfavorable process. And as a result, more energy is needed to remove the electron, and therefore the ionization energy of nitrogen is higher than oxygen. Okay, and this is why you see that nitrogen will have a higher ionization energy in comparison to oxygen because of the half-filled orbital at the 2p. Alright, now we're going to move on to the period 3. So in the period 3, we also see a similar cases that appears in period 2, where the anomaly happened at group 2 and group 13. So for group 2 in period 3, we have magnesium, and for group 13 at period 3, we have aluminium. So similar thing, we need to look into the electronic configuration. So for magnesium, we have 1s2, 2s2, 2p6, which is and 3s2, which has 12 electron altogether. And then for aluminium, it has 13 electron. So the electronic configuration is going to be 1s2, 2s2, 2p6, 3s2, and 3p1. So in terms of orbital diagram, you know that the orbital diagram for magnesium will have a completely filled orbital at the 3s. Meanwhile, for aluminium, it's going to have a partially filled orbital at the 3p part here. So the completely filled orbital at the 3s in magnesium is more stable than the partially filled orbital of 3p in aluminium. Hence, removing an electron from the completely filled orbital of 3s in magnesium makes the atom less stable, which is an unfavorable process. Hence, more energy is needed to remove one electron from a stable state. Therefore, the ionization energy of magnesium is going to be higher than aluminium. Alright? Similarly, we can also explain that for phosphorus and sulfur. So phosphorus is in group 15, the sulfur is in group 16. So we're going to look into the electronic configuration. So phosphorus will have 15 electrons. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p3, which is half-filled orbital. And then for sulfur, it's going to have 16 electrons. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p4. And here is the orbital diagram. So phosphorus will have a half-filled 3p orbital. So you can say that the half-filled orbital of 3p in phosphorus is more stable than the partially filled orbital of 3p in sulfur. And removing an electron from the half-filled 3p orbital in phosphorus makes the atom less stable, which is unfavorable process, and hence more energy is needed to remove the electron. And as a result, the ionization energy of phosphorus is a little bit higher than sulfur. Alright, now we're going to look into the variation of the first ionization energy down the group. So as what you have learned, across a period, the attraction between the nucleus and the valence electron increases. Okay, and as a result, the ionization energy will increase as well. However, down the group, the size will get increases. So the distance between the valence electron and the nucleus is very, very far apart. So you will know that down the group, it is easier to remove an electron. So when it is easier to remove an electron, you can say that the ionization energy decreases down the group. Okay, because the size is much, much larger. Okay, so lagi senang nak keluarkan electron. So you can say that down the group, when the principal quantum number or the number of shell increases, you will know that the screening effect will be increases as well because there are more number of electrons. And as a result, the distance between the valence electron and the nucleus will get larger. And this causes the attraction between them to be weaker and the atomic size increases. So there are going to be less energy that is required to remove an electron. Okay? And thus, the ionization energy decreases down the group. And you know that a smaller atom will be more difficult to remove because it is closer. So when it is a larger gap, it is easier because the attraction is weaker. Alright? So I think that's all for this video. See you again some other time. Bye!